Hello and good morning. Welcome to Vincent Statistics, where my name is Dayap Vincent, Chemical Engineering 1 from Section A13. And we will be discussing on Episode 3, Spectroscopy Statistical Analysis. So if you can remember from Episode 1, I discussed how to solve statistics or statistical analysis. Episode 2 is more on spectroscopy using Beer-Lambert's law. Episode 3 is more of an integration of Episode 1 and Episode 2 in one problem. Therefore, before everything else, let us discuss the objectives for today's video. Number 1, to answer Chapter 28, Number 15 in Fundamentals of Analytical Chemistry 9th edition Scoob. Number 2, to comprehend statistical solutions. And number 3, to conjoin statistics and spectroscopy in one full application. I would like to give an author's note that we will try to solve as much problems numerically as possible, meaning that we will try to hinder ourselves using Excel and try to focus on pen and paper mathematics and statistics to solve these questions. And we will only use Excel tools if the statistical analysis done is too heavy, such as graphing, F-test, T-test, so on and so forth. But spoilers, there will be no F-test or T-test, only just graphing, so we only use Excel for the graph. And of course, before everything else, I need to show you some formulas and sample calculations. Though I already discussed this in Episode 1, there's nothing to hurt when we're discussing this again. So, I have the sample data, and the mean of the x is simply the number of data given over the number of data. Same din in the y version. For SXX, it's just simply the summation of the data of x squared minus the summation of the data, where you'll square that, over the number of data. Same din for y, except it's all y variance. And lastly, SXY is equal to the summation of x times y data minus the summation of x times the summation of y over the number of data. Of course, since we're doing this, we will use the equation of the line, where you will find the slope of the line, or m, equal to sxy over sxx. The y-intercept is equal to the mean of y minus the slope times the mean of x. And we'll find the r, or the line coefficient, if we can, and we use this to determine if the equation is actually linear or not. Through this formula, sxy over the square root of sxx times syy. And of course, we need to find the standard deviation of the line components. So the standard deviation of the slope is simply the square root of sr squared over sxx. And we can find sr using this formula. Square root of syy minus slope squared, or m squared, times sxx over n, or the number of data, minus 2. And we can find sb by sr times the square root of the summation of x squared, or x data squared, minus r over the number of data multiplied by the summation of the x squared minus the summation of the x, and we will get that value by squaring it. And of course, confidence intervals, but we're not going to use that much confidence intervals because the problem does not require it. But still, I'll explain that the confidence interval is just simply the slope plus or minus the t-score at 95% confidence times the standard deviation over the square root of the number of trials. It's the same for the confidence interval of the y-intercept. In short, in order to find the confidence interval of anything, it's just simply the original or the mean value plus or minus the t-score at whatever percent is assigned to you. Normally in chemistry, it's used by 95% times its standard deviation over the square root of the number of data given. And you can find the t-score using this formula based on the degrees of freedom, which is n minus 1, so if 5 minus 1, 4, and at a 95% confidence interval, it would be 4.604, if I'm not mistaken. Therefore, let's put these data into action, where the mean of x will be 3.333, the mean of y will be 25, sxx would be 5, syy would be 500, sxy is 50. The equation of the line, based on the calculations and formula, the slope is 10, the y-intercept is 0, and the line coefficient is 1. This means that the data is linear. We have SR equals 0, SB equals 0, and SM equals 0, and the confidence interval is 10 plus or minus 0 for the slope, and B 0 plus or minus 0. Now we have seen everything in action. Let us now go to the question. We only have one question for today, but it's a very, very long question, and I'll be discussing it in detail with you all today. So we'll have the first question. Chapter 28, number 15. The copper in an aqueous sample was determined by atomic absorption, flame spectrometry. First, 10 milliliters of the unknown were pipetted into each of 550 ml volumetric flasks. Various volumes of a standard containing 12.2 ppm copper solution were added to the flask, and the solutions were then diluted to volume. A table of numeric data is given. So we have the unknown, which is 10 milliliters, standard, which is with intervals of 10 from 0 to 40, so 0, 10, 20, 30, 40, and their absorbance is given. We have the requirements. A. Plot absorbance as a function of volume of standard. B. Derive an expression relating absorbance to the concentrations of standard and unknown, which is Cx and Cs, and the volumes of the standards and unknown, Vs and Vx, as well as the volume to which the solutions were diluted, which is the volume total, or Vt. C. Derive expressions for the slope and the intercept of the straight line obtained in A in terms of the variables listed in B. Show that the concentration of the analyte is given by the relationship Cx equals Bcs over Mvx, where M and B are the slope and the intercept of the straight line in A. Determine the values for M and B by the method of least squares. Calculate the standard deviation of the slope and intercept in E. And lastly, letter G, calculate the copper concentration in ppm Cu in the sample using the relationship given in D. So A, B, C, D, E, F, G, there are seven things to find. And of course, this is just one question, but as I said, this question has a lot of requirements. So that's why this video is only for one question only. But fear not, we will try to answer this with much details as I can possibly provide to you all. So let's start first with the first question. Plot absorbance as a function of volume of standard. So we have this table, however it says here plot absorbance as a function of volume of standard. Therefore, we'll only need to plot this part of the data table. So of course, as I said, we will need to do it numerically in order to learn how to do it by hand, statistics or linear squares equations. So numerically, we will have XY data. So based on the table given, we have the mean, which is 20, SXX is 1000, and let me skip it here. Alright, so based on the data, the standard will act as the x-axis, the absorbance will act as the y-axis. Therefore, based on the formulas from the sample calculation and the sample formulas, we'll have the following data. The mean of the x value is 20. The mean of the y value is 0.3784. SXX will have a value of 1000, SYY will have a value of 0.0776, SXY will have a value of 8.81, the slope, or M, will have a value based on the formula 0.0088. The y-intercept based on the formula given, we calculated a y-intercept of 0.2024. And lastly, we need to find if the data is linear or not. So based on the formula, we substitute, we have an R value of 1.001. This is great because since the value of R is 1, this data is considered linear. Putting all the variables into the line equation y equals mx plus b, we calculated that the line expression for this table data is y equals the slope x plus y-intercept, or y equals 0.0088x plus 0.2024, and we have proven that this data is linear. Using Excel, of course, graphically, this is how it looks like. So as you can see, it's actually linear, a straight line, and the linear equation is similar, or actually very identical to our calculated one. This means that what we calculated and what Excel calculated, the line equation, is very accurate and very similar. This means that what we calculated is not wrong. It is correct. And it, of course, proven linear, graphically and numerically. So, table of data for convenience's sake. Letter B. Derive an expression relating absorbance to the concentrations of standard and unknown, CS and CX, and the volumes of the standards and unknown, VS and VX, as well as the volume to which the solutions were diluted, or VT. So, let us remember that the absorbance formula is given as this. And as I said from the previous video, that we do not have any light intensity given. We only have the absorptivity, the cell pathway, and the concentration. So we'll use simply A equals ECL, or epsilon CL. We were given data, but thinking about it logically speaking, that the absorbance is a combination of two absorbances. Since we put the copper solution with 0 at L, then we just keep on doing standard addition of the standards. That means that the absorbance will lead to a result that has a mixture of the absorbance of standard plus the absorbance of copper. So this is how, logically speaking, the absorbance total is simply the absorbance of the standard plus the absorbance of the copper. And if we know that the formula for absorbance is epsilon CL, then we can just exchange that into the equation. Let's also remember that we diluted, or the copper solution excuse me, keeps on being diluted as per addition of the standard. Therefore, we'll have this dilution factor, where in the standard we have the volume of the standard over the volume total, which is the volume of the standard plus the volume of the copper, which is Vx. And for the absorbance of the copper, it's just simply Vx over Vt, where Vx is the volume of the copper. When we combine the epsilon CL equals A and the A equals A standard Vs over Vt plus A copper Vx over Vt, we'll have this expression. Since we know that absorbance has a formula of epsilon concentration times pathway, we can just substitute the A formula in the A variables of the standard in the copper, thereby having this expression: the absorbance, or the total absorbance, equals the epsilon concentration and pathway of the standard times its dilution factor plus the epsilon concentration and the pathway of the unknown of the copper solution times its dilution factor. Let's further simplify. So we have this expression. So since they're both using the same machine, that means they're both using the same cell or the same cuvette. That means that the pathway used is just the same. So that means there's no need for LS or LX. We can just simply say L. And we also identified that when we multiply the volume and the concentration, we'll get a moles, or some sort of mole unit, since it's given logically speaking, because normally in chemistry, when you're multiplying volume and the concentration, you will get a value of moles. So let us factor in the molar absorptivity, or epsilon S times the pathway over Vt plus the epsilon X times the pathway over Vt in the respective areas. Since we need to find a way to relate the volume of the standard and the volume of the unknown with the concentration of the standard and the concentration of the unknown, that's why we'll have Vs and Cs in one parenthesis and Vx and Cx on one parenthesis. And let's just assign ESL over Vt as K and EXL over Vt as K as well, thereby having this expression VSCS times K plus VXCX times K. And this is what the question is finding, because look, the question finds or requires that we need to find an expression that relates the absorbance of the standard and unknown CS and CX. and the volumes of the standards and unknown, Vs and Vx. Is there Cx and Vx here? Yes. Is there Cs and Vs here? Yes. We have absorbance and we have K, therefore we have satisfied this equation. And yes, this is the bolded answer. Letter C. Derive expressions for the slope and the intercept of the straight line obtained in A in terms of variables listed in B. So, let us say that what we computed is true. Then how can we turn this into a line equation? So simply put, let's just let some variables be assignment. Let M, or the slope of the line, equals the K times CS. Let B, or y-intercept, equals K Vx Cx. And let Y equals A. Using the assignments of variables, we will have a line equation Y equals M times the volume of standard plus B. The reason why only the volume of standard is a variable here is because the volume of unknown is constant, the concentration of the standard is constant, and the only thing that varies is the volume of the standard. That's why the volume of the standard is left as a variable in the line equation. By the way, the absorbance, though it's also a varying data, it's the result of the combination using the line equation of the volume of the standard, concentration of the standard, and the volume of the unknown and the concentration of the unknown that can find the absorbance. Letter D. Show that the concentration of the analyte is given by the relationship Cx equals BCS over MBx, where M and B are the slope and the intercept of the straight line A. So simply put, we need to prove that Cx equals BCS over MBx. So remember that we let M equals KCS and we let B equals Vx, Cx times K. Let's isolate K in the M. So we have K equals M over Cs, and for the B, we have K equals B over Vx Cx. Since they both have the same variable equality, which is K, we can just say that B over Vx Cx equals M over Cs. And we need to find Cx. Let's isolate Cx, and we will have, using algebra, this expression. Cx equals BCS over MVx. And what is it's given? So we need to prove that the relationship of the unknown concentration equals BCS over MVx. And as you can see, it's already proven mathematically. Letter E. Determine the values for M and B by the method of least squares. We already done that earlier. So, what we calculated that the slope, or M, is 0.0088 and the y-intercept, or B, calculated is 0.2024. We need to find letter F. Calculate the standard deviation for the slope and the intercept, or SB and SM. So we have the M, B, and R calculated. We have X average, YX mean, Y mean, SXX, SYY, SXY calculated. And we have the number of data is 5. So using the formula, the standard deviation of the R is the square root of SYY minus slope squared SXX over N minus 2. We'll have a value of 0.0073. We will use this value to calculate SB. SR equals the square root of the summation of data of X squared over the number of data multiplied with the summation of the data X squared minus the summation of data X, and you will square that value. You will have a value of 0.7746, and SM, you will use the formula for SM, the square root of SR squared over SXX, which have a value of 0.0002. And we have calculated the standard deviation of SM, 0.0002, and SB, 0.7746. G. Lastly, the final question, calculate the copper concentration in parts per million copper in the sample using the relationship given in D. So we have Cx equals BCS over MBx. If we let our variables assignment, Cx equals the concentration of copper, CCU, The y-intercept we calculated is 0.2024, the slope is 0.0088, the volume of the unknown based on the question is 10 milliliters, and the concentration of the standard is 12.2 parts per million. Thereby, substituting every variable given, 0.2024 12.2 over 0.0088 times 10 milliliters will have a concentration of 28.06 parts per million. And this is the final answer. Of course, let's go back to our objectives. We answered chapters 28 and number 15 flying colors with every detail that I can give and proven. We comprehend statistical solutions, and we conjoin statistics and spectroscopy in one flow, stat, and application. Again, Vincent Statistics. My name is Vincent M. Dayap, Chemical Engineering First Year, A13, Episode 3, Spectroscopy, Statistical Analysis, and I would like to thank you all for listening to my presentation. Thank you, have a good night, and enjoy.